Hi Anandal, this is U. Srinivas, Senior Chemistry Faculty, Sri Chaitanya Gosala Campus, Vijayawada. Last time we had discussed chemical kinetics. In that, we discussed the subtopic effect of temperature on the rate of the reaction. Hope you followed the same. And today we are going to discuss abnormal colligative properties from the solutions. Abnormal colligative properties from the solutions. Okay, my dear students, before we discuss abnormal colligative properties, let us discuss what are colligative properties. Colligative properties are the properties of dilute solution, or we can say the properties of the solution that depends on number of particles of the solute. That depends on number of particles of the solute, but independent of nature of the solute, which is nothing but identity of the solute. The value of the colligative property directly proportional to number of particles of the solute. Value of any colligative property directly proportional to number of particles of the solute, but independent of nature of the solute, nothing but identity. Okay, let us discuss the colligative properties. How many colligative properties that we have? We have 4 colligative properties. What are they? Relative lowering in vapor pressure. Relative lowering in vapor pressure, RLVP. This relative lowering in vapor pressure is nothing but delta P by P naught is equal to mole fraction of the solute. What is the delta P? Delta P is the difference between vapor pressure of the pure solvent and vapor pressure of the solution. Delta P is the difference between vapor pressure of the pure solvent and vapor pressure of the solution that containing a non-volatile solute. This is, you can write P or you can also write PS. Vapor pressure of the solution that containing non-volatile solute by P naught, which is equal to mole fraction of the solute. And moreover, my dear students, the colligative property is applicable only when the solute is a non-volatile. Solute is non-volatile, right? And here, what is the delta P? P naught minus PS. And what is P naught? Vapor pressure of the pure solvent. Vapor pressure of the pure solvent. And what is this P or PS? Vapor pressure of the solution that containing non-volatile solute. Solution with non-volatile solute. NVS means non-volatile solute. This is LVP, my dear students. P naught minus P is nothing but LVP. This P naught minus P is lowering in vapor pressure. Lowering in vapor pressure. Where P naught is vapor pressure of the solvent. The ratio between lowering in vapor pressure and vapor pressure of the pure solvent is relative lowering in vapor pressure. Relative lowering in vapor pressure, which is equal to mole fraction of the solute. Okay. And what is the another colligative property? Elevation in boiling point. Elevation in boiling point. For that, the expression is delta TB is equal to Kb into molality. Delta TB is equal to Kb into molality. What is the delta TB? Delta TB is the difference in the boiling point. Here, the boiling point of the solution is always more than that of the boiling point of the pure solvent. The boiling point of the solution that containing non-volatile solute is more than that of boiling point of the pure solvent. Since vapor pressure is inversely related to the boiling point, since P naught value dominates over the PS, TB dominates over the TB naught. Vapor pressure of the pure solvent is more, boiling point of the solution is more. Why? Because boiling point is inversely proportional to vapor pressure. So that the delta TB can be written as TB minus TB naught. And what is this Kb? Kb is molar elevation constant. Molar elevation constant. Are also known as ebullioscopic constant. Also called it as ebullioscopic constant. Where Kb is molar elevation constant or ebullioscopic constant. And the value of Kb is independent of the concentration. It depends only on the nature of the solvent. It depends on the type of the solvent. If solvent change, the Kb value shall change. The value of the Kb depends on the nature of the solvent. Kb value is independent of the concentration of the solution. This is an important point, my dear students. Kb value is independent of the concentration of the solution. Independent of the concentration of the solution. Depends only on the nature of the solvent. So coming to another colligative property, depression in freezing point. Depression in freezing point. Depression in freezing point. That can be delta Tf is the symbol for the depression in freezing point, which is equal to Kf into molality, where Kf is molar depression constant. Molar depression constant. Molar depression constant, or also known as cryoscopic constant. Cryoscopic constant. Just like Kb, Kf doesn't depend on the concentration of the solution. Kf independent of concentration of the solution. Kf depends on the nature of the solvent, just like Kb. It depends only on the nature of the solvent. Depends on the type of the solvent. Just like Kb. Kb is molar elevation constant, Kf is molar depression constant. And here delta Tf is, where delta Tf is Tf naught minus Tf. Can be delta Tf. Tf naught minus Tf. What is the Tf naught? Tf naught is freezing point of the pure solvent. If it is a water, freezing point of the water is 0 degrees C, or we can say 273 Kelvin, where Tf is freezing point of the solution containing NVS, non-volatile solute. It is directly proportional to vapor pressure. My dear students, vapor pressure and freezing point proportional to each other, which is inversely proportional to boiling point, right? Where M is the molarity of the solution. Just like the previous expression. And we have one more colligative property, nothing but the osmotic pressure. Osmotic pressure. The expression is pi is equal to CRT, or we can also say CST. The expression of the osmotic pressure. Osmotic pressure. Pi is equal to CRT, where C is concentration expressed in molarities. Concentration expressed in molarities, mole per liter, where R is universal gas constant you can take. Why? Because since diluted solutions can behave as the ideal gases, you can take a solution constant value as the ideal gas constant. Actually, here we can able to write, yes instead R. But since we are discussing diluted solution properties here, since diluted solutions behaves as the gases, you can take R value as the solution constant, right? Where T is absolute temperature. This is about the colligative properties, my dear students. But the value of any colligative property directly related to number of the particles of the solute. Normal value of the colligative property directly related to number of particles of the solute. Number of particles of the solute. Dear students, this holds very good for a kind of non-electrolytic, non-volatile solutes like urea, glucose, sucrose, that and all. All these are non-electrolytic, non-volatile solutes. Urea, glucose, sucrose, non-electrolytic, non-volatile solutes means they do not undergo either association or dissociation. They do not undergo either association or dissociation with the given solvent. Such kind of the solutes are non-electrolytic, non-volatile solutes. If such kind of the non-electrolytes are used as the solutes, then we can take normal colligative property as the experimental colligative property. No difference between the experimental colligative property and the normal value of the colligative property. Observed colligative property, normal value of the colligative property will be the same in case of non-electrolytes such as urea, glucose or sucrose, that and all. Suppose if solutes can undergo either dissociation or association, if the solutes can undergo either dissociation or association with the solvent, then number of particles would change. Therefore, the value of the colligative property shall change accordingly. Did you get this point, my dear students? If the solute is non-electrolytic, non-volatile like this, if the solute doesn't undergo any dissociation or association, then normal value of the colligative property, experimental value of the colligative property, both will be the same. For this, experimental colligative property, in the sense the observed colligative property is equal to normal value of the colligative property. Both values will be the same. But when the solutes undergo either dissociation or association with the solvent, for them experimental colligative properties would be different from that of normal value of the colligative properties. Let us discuss the abnormality in colligative properties. See, the abnormality in the colligative properties can be explained in terms of a factor called Van 't Hoff factor. What is the Van 't Hoff factor? The abnormality in the colligative properties. Why we can discuss abnormality in the colligative properties? Because all the solutes may not be likewise. Some solutes may undergo either association or the dissociation with the solvent. For them, the number of the particles would change. Automatically, the value of the colligative property shall change. For that purpose, we need to discuss the abnormal value of the colligative properties. So that from this we can understand that solute may change in particular solvent in two ways. Solute may change in particular solvent in two ways. What are that ways? We'll discuss now. By dissociation, by association. Dear students, during the dissociation of the solute, the number of the particles would increase. During the association, the number of the particles would decrease. So, during the dissociation, number of the particles would increase, and in the association, the number of the particles would decrease. So, whenever number of particles increases, the abnormal value of the colligative property shall dominate over the normal value of the colligative property. Why? Because abnormal value of the colligative property is directly proportional to number of particles of the solute after dissociation or association. After dissociation or association. Abnormal value of the colligative property directly related to number of the particles of the solute after dissociation or the association. After dissociation, you know this, you came to know this, and the number of the particles would increase. So that as number of the particles increase, abnormal colligative property increase over the normal value of the colligative property. See, this abnormal colligative property also known as the observed colligative property. This normal colligative property also known as the theoretical colligative property. Theoretical colligative property. But after association, the number of the particles would decrease, so that abnormal value of the colligative property value is less than the normal value of the colligative property. See, already we discussed at this point, the abnormality in the colligative properties is explained in terms of a factor called what? Van 't Hoff factor. What is the Van 't Hoff factor? Van 't Hoff factor is denoted by the symbol I, which is the ratio of Van 't Hoff factor. Van 't Hoff factor denoted by a symbol I, which is the ratio of abnormal colligative property to normal value of the colligative property. abnormal value of the colligative property to normal value of the colligative property. So that we can say during the dissociation, I value is greater than 1. And during the association, since abnormal value of the colligative property value is lesser than the normal value of the colligative property, I value less than 1. Did you understand this? I is the symbol of the Van 't Hoff factor. Van 't Hoff factor is explained the abnormality in the colligative properties, the magnitude of the abnormality in the colligative properties. If I greater than 1, that is called the dissociation. During the dissociation of the solutes, I greater than 1. During the association of the solutes, I less than 1. Right? And I mentioned previously for the solutes like the urea, glucose, sucrose, for that and all, I value is exactly equal to 1. Why? Because for them, the experimental value of the colligative property and normal value of the colligative property both would be the same. So that I value is equal to 1. For the urea, glucose, sucrose, I is equal to 1. In the question itself, when you find such kind of the solutes, urea, glucose or sucrose, or if it is given like that non-electrolytic, non-volatile solute, you can mention I value is equal to 1. So that you can feel that comfortably, feel that it is a normal value of the colligative property. There is no abnormalities can be seen. So I greater than 1 for the dissociation, I less than 1 for association. Okay. So let us find the relation between alpha and I during the dissociation of the solute now. Let's find the relation between Van 't Hoff factor I and degree of dissociation of the solute during the dissociation. And during the dissociation of the solute, let us take a solute is A. Upon dissociation, if it gives n moles of the ions, upon dissociation, if it gives n moles of the ions, I'm taking initially if 1 mole of a solute A, and initially if 0 moles of ions are there, and after some time if alpha is the degree of dissociation of the solute, and the number of moles of an electrolyte would be 1 minus alpha. For n moles of the ions, the number of moles of the electrolyte would be n alpha. Then the total number of moles would be 1 minus alpha plus n alpha. By taking alpha as the common here in minus 1. This is the number of the particles formed after the dissociation, which is nothing but abnormal value of the colligative property. This is the number of moles taken initially, which is nothing but normal value of the colligative property. So let us find the Van 't Hoff factor. Told you, Van 't Hoff factor is the ratio between abnormal value of the colligative property to normal value of the colligative property. So that 1 plus alpha of n minus 1 by 1. From this, we can have alpha is equal to I minus 1 by n minus 1. Thus is the relation, my dear students, where alpha is degree of dissociation of the solute. Degree of dissociation of the solute. Where I is Van 't Hoff factor. N is number of particles formed during the dissociation, or number of the particles formed after dissociation. During the dissociation, number of the particles formed, that's called N. That's about dissociation, my dear students. So let us discuss the relation between Van 't Hoff factor as well as alpha for the association of the solute. Taking n molecules of A here, when n molecules of the A uniting together and giving off a joint molecule AN. Suppose if I take these n molecules of the A as 1 mole and this would be the 0, and alpha will be the degree of association of the solute with the given solvent, and this would be 1 minus alpha, and this would be alpha by n. Let us calculate the total number of moles here. That is nothing but 1 minus alpha plus alpha by n. Taking the alpha as the common here, 1 by n minus 1. Finding a Ventov factor here, it is the ratio of abnormal colligative property to normal value of the colligative property. Here this is called the normal value of the colligative property, normal value. This is abnormal value of the colligative property. So 1 plus alpha of 1 by n minus 1 by 1. After rearranging all these, we can have what? Alpha is equal to 1 minus I by 1 minus 1 by n. 1 minus I by 1 minus 1 by n. That's the formula for the association of the solute. And this is the relation between alpha and I for the dissociation of the solute. That is the relation between alpha and I for the association of the solute. And suppose if alpha is not yet mentioned, otherwise, if alpha is given as 100%, if alpha not yet mentioned, or if alpha is given as 100%, then we can take I value as the n during the dissociation. Then number of the particles formed after the dissociation can be taken as Ventov factor. When if alpha not mentioned, or if alpha value is taken as the 1. If the percentage of alpha is 100%, or if alpha is the 1, or if alpha not mentioned, then I value can be taken directly as the number of the particles formed after the dissociation. Similarly, here also, if alpha not mentioned, otherwise if alpha value is equal to 1. Since this is the association and I value can be taken as 1 by n here. Did you get this point, my dear students? Most of the students will get a doubt here. When we can take number of the particles I directly, when we cannot take. This is I am explaining right now. See, whenever alpha value not mentioned, or if alpha value is mentioned as the 1, for association I is equal to 1 by n. For the dissociation I is equal to n. For the dissociation I is equal to n. For the association I is equal to 1 by n. This is about concept, my dear students. And let us write abnormal colligative properties once. Now I am going to give abnormal colligative properties by introducing Ventov factor I. RLVP, relative lowering in vapor pressure, delta P by P naught is equal to, introducing Ventov factor here, I into mole fraction of the solute. I into mole fraction of the solute, where I is Ventov factor. Similarly, elevation in boiling point, delta TB is equal to, introducing Ventov factor here, I into Kb into molality. Depression in freezing point, delta TF is equal to, introducing Ventov factor, I into Kf into molality. Osmotic pressure, pi is equal to ICRT. These are modified colligative properties or abnormal colligative properties. Let us solve some numericals related to these concepts. Dear students, of the following 0.1 molar aqueous solutions, which one will exhibit largest freezing point depression? Largest freezing point depression. My dear students, you remember this, all 4 colligative properties and boiling point directly proportional to number of the particles of the solute. All 4 colligative properties. All 4 colligative properties. What are the 4 colligative properties? RLVP, EBP, DFP, OP are 4 colligative properties and boiling point directly related to number of the particles of the solute. But freezing point and vapor pressure, freezing point or vapor pressure, these are not colligative properties, inversely proportional to number of the particles of the solute. inversely proportional to number of particles of the solute. This is very, very important, my dear students. All four colligative properties and boiling point directly proportional to number of the particles of the solute. But freezing point or vapor pressure inversely proportional to number of the particles of the solute. With use of the same, we can find. This here it is asking about largest freezing point depression. Freezing point depression is a colligative property. Colligative property directly proportional to number of the particles of the solute. Since alpha is not yet mentioned here, I value can be taken as the N value. So, very first option, Al to SO4 taken 3 times. When you split this compound, it splits into 2Al plus 3, 3SO4 minus 2. How many Al plus 3 ions are there? 2. How many SO4 minus 2 ions are there? 3. 2 plus 3, 5. So, what is the high value here? 5. Can we take high value directly here? We can. Since alpha not yet mentioned, we can take I value as the number of the particles. So, what's the I value here? 5. K to SO4. When you split this, 2K plus SO4 minus 2. 2 plus 1. This is 2, this is 1. What is the I value here? 3. KCl. K plus Cl minus. What's the I value here? 2. And this is glucose, C6H12O6. It is a non-electrolytic, non-volatile solute. It do not undergo either dissociation or association. I value is equal to 1. Since this is the colligative property, since they are asking about largest freezing point depression, higher the number of the particles of the solute, higher is the magnitude of the colligative property. So, which is having more number of the particles here. Particles of the solute here, Al to SO4 taken 3 times. So, that is the right option, my dear students. Did you understand? Depression in freezing point is a colligative property which is directly proportional to number of the particles of the solute here. Coming to the next one. If molarity of the dilute solutions is doubled, the value of the molar depression constant Kf will be. In the concepts itself, we discussed at this point. Kf is a molar depression constant or cryoscopic constant. It's a constant, molar depression constant. It is independent of concentration of the solution. Independent of the concentration of the solution. It depends only on the nature of the solvent. Depends on the type of the solvent. For water, we have 1 Kf. For benzene, we have the different Kf. When type of the solvent change, the Kf value shall change. Kf doesn't depend on the concentration of the solution. It only depends on nature of the solvent. So, it will be unchanged. Coming to the next one, my dear students. The following solutions were prepared by dissolving 10 grams of the glucose in 250 ml of water, 10 grams of urea in 250 ml of water, and 10 grams of the sucrose in 250 ml of water. The decreasing order of the osmotic pressure of these solutions is. You can take a normal osmotic pressure itself here. Why? Because whatever the given solutes are non-electrolytic, non-volatile solutes. Glucose, urea, sucrose, all these are non-electrolytic, non-volatile solutes. For them, I is equal to 1. So that writing the expression, I no need to represent here, pi is equal to CRT, where C is the molarity. Right? And at a given temperature, T is constant or already constant. So, pi value is directly related to molarity here. Higher the concentration, higher will be the osmotic pressure here. So, concentration, how can we calculate? Towards the molarity. And of course, the volume also same. Writing about the molarity of the glucose. Molarity of the glucose, M1. What is the weight of the glucose? 10 by molecular weight of the glucose, 180 into 1000 by what is the volume given in ml? 250 ml. Coming to the molarity of sucrose. What is the second one? The molarity of urea. 10 by 60 into 1000 by 250. The third one, molarity of the sucrose. 10 by 342 is the molecular weight of the sucrose. 1000 by 250. What is the uncommon here? Uncommon one is the molecular weight of the solute, 180, 60, 342. Since it is there with the denominator, lesser the value in the denominator, higher will be the osmotic pressure. Higher will be the concentration, thereby higher will be the osmotic pressure. So that it is related to, say, if it is M1, which is related to pi 1. Say this is the M2, which is related to pi 2. Say this is M3, which is related to pi 3. So which is the higher? Pi 2 value will be the higher. So pi 2 is greater than, thereafter pi 1, 180 is greater than, thereafter pi 3. Here they would have taken P instead pi, so that I am mentioning P2 greater than, P1 greater than P3. Understand, my dear students? Hope you understand. Coming to the next one. Which of the following aqueous solutions has the highest vapor pressure at 300 Kelvin? Highest vapor pressure. Told you, my dear students, see freezing point vapor pressure. I am not saying about lowering in vapor pressure or depression freezing point. They are the colligative properties. I am saying only vapor pressure freezing point. Vapor pressure or freezing point, inversely proportional to number of the particles of the solute. This is not the colligative property, my dear students. Vapor pressure or the freezing point, inversely proportional to number of the particles of the solute. Go through the options. Ne3PO4. Alpha is not yet mentioned. You can take I value as the number of the particles here. Ne3PO4. When you split this, 3Na plus PO4 minus 3. How many particles it is? 3Na plus 1 PO4 minus 3. Together it is 4 particles. 1 molar calcium chloride. Since concentration is the same here, we are discussing only the electrolytes. Calcium chloride. Ca plus 2, 2Cl minus. 1 Ca plus 2, 2Cl minus. 1 plus 2, 3 particles. KNO3. 1 mole K plus, 1 mole NO3 minus. 1 plus 1. Number of the particles would be 2. This is glucose. Glucose is non-electrolytic, non-volatile solute. I value is equal to 1. Since we are asked to calculate highest vapor pressure, since number of the particles is inversely proportional, glucose will have a higher vapor pressure relatively. Glucose. Next one, my dear students. 1 molar aqueous solution of an electrolyte E2B3 is ionized 60%. The boiling point of the solution at 1 atmosphere is Kb of water is mentioned as 0.52 Kelvin kg per mole. Here Kelvin should be there. 0.52 Kelvin kg per mole. What is the formula of the elevation and boiling point? Delta Tb is equal to, introducing Van factor here, I into Kb into molarity. Delta Tb is equal to I Kb n. Right. I value, how can we calculate? It is mentioned as 60%, which is nothing but the percentage of dissociation. Alpha value is mentioned 60%. From the alpha value, we can able to calculate I value. How? Since this is the dissociation, alpha is equal to I minus 1 by n minus 1. This is the formula that we can apply in order to calculate Van factor whenever alpha is given. 60% in the sense alpha value can be taken as 0.6 is equal to I minus 1 by n is the number of the particles formed during the dissociation of A2B3 electrolyte. A2B3 upon ionization giving off 2A plus 3 plus 3B minus 2. How many particles it is? 2A plus 3, 3B minus 2. Together it is 5 particles. And value is the 5. So 5 minus 1. Okay, my dear students, this 5 minus 1 is the 4. 4 into 0.6, 2.4. I minus 1 is 2.4. Then I is equal to 3.4. I is what? 3.4. Using 3.4 I value here, 3.4 Kb given itself, 0.52 and molality is 1 molar mentioned, which is the delta Tb value. So, and its value is an approximately 1.76, my dear students. 1.76. Expanding delta TB here. Delta TB is nothing but TB minus TB naught. TB naught means boiling point of the pure solvent, boiling point of water. What is the boiling point of water? 373 you can take is equal to 1.76 Kelvin. Then boiling point of the solution will be 373 plus 1.76. That is nothing but 374.76 Kelvin. 374.76 Kelvin. Coming to the next one, my dear students. Which one of the following electrolytes has the same value of the Van Hoff factor as that of aluminum sulfate if all are 100% ionized? Clearly mentioned, if all are 100% ionized, in the sense you can take I value as the N value for the dissociation. And it is mentioned aluminum sulfate has how many particles? What's the I value of the aluminum sulfate? Split this, 2Al plus 3 SO4 minus 2. Together it is 5 particles. So I value is the 5. Let us go through the options. Let us find from which I value will be equal to 5. Coming to the very first one, K4FeCN6. This is the complex compound, my dear students. How can we separate the ions from the complex compound? Whatever the ions are there outside the square bracket that can be ionizable. 4K plus and one complex anion FeCN taken 6 times to the minus 4. 4K plus one complex anion. 4 plus 1. What's the I value here? 5. Which is exactly correlates with the same. When you go through the remaining options, you may not get I value as the 5 because K2SO4. When you split this, you will get I value as the 3. 2K plus SO4 minus 2. K3FeCN6. Told you no. 3K plus and 1 FeCN6 of the minus 3. 3K plus FeCN taken 6 times of the minus 3. This is 3, this is 1. 3 plus 1 which is equal to 4. This is also aluminum nitrate 1 Al plus 3, 3 NO3 minus ions, NO3 minus, 1 plus 3, 4. Right option is first option, K4FeCN6. Okay, my dear students. Next question. Which of the following is dependent on temperature? These are all previous year questions, my dear students. Which of the following is the dependent on the temperature? Molarity, mole fraction, weight percentage, molarity. My dear students, except molarity, all the remaining doesn't depend on the temperature. Why? Because molarity is volume based. All the remaining are weight based. It is weight to volume. This is weight to volume. Number of moles with respect to volume. All the remaining 3 are weight based. Since it is the volume based, since molarity is the volume based, molarity depends on the temperature. Since molarity is the number of moles per unit volume, since volume is there with the denominator, as temperature increases, volume increases, molarity decrease with rise of temperature. Molarity decrease with rise of temperature. Okay, my dear students, coming to the next one. In 1 molar solution that contains 0.5 moles of the solute, there is, in 1 molar solution that contains 0.5 moles of the solute, there is, means how to get 1 molar solution from 0.5 moles of the solute with use of the options. That's the question. So it is given very clearly that molarity, what's the formula of the molarity? Molarity is number of moles of the solute in 1 kg of the solvent. Number of moles of the solute in 1 kg of the solvent. Right? And this can also be written like this. Molarity is equal to number of moles of the solute into 1000 by weight of the solvent in grams. Weight of the solvent in grams. Weight of the solvent in grams. Right? Since they have mentioned molar, we have to compare the number of moles with 1 kg of the solvent. since they are asking about 0.5 moles of the solute, just by going through the options, look at this, my dear students, 100 ml, this is out of the competition because that is the molality, weight to weight relation. So 500 ml, these two out of the competition. 1000 grams, 500 grams, which would be the right option? If it is 1000 grams, that would be 0.5 molar solution, but they are asking 1 molar solution. In order to get 1 molar solution, the weight should be 500 grams. Molality is equal to number of moles of the solute, 0.5 they mentioned, 1000 by weight of the solvent, 500. We'll get that 1 molar solution. Okay, my dear students. Coming to the next one. 0.002 molar solution of NaCl having degree of the dissociation of 90% at 27 degrees C has osmotic pressure equal to. Since electrolyte that they have mentioned, since this can undergo the dissociation with the water, so we have to use abnormal colligative property. Pi is equal to ICRT. And since alpha value is mentioned as 90%, percentage of alpha as the 90%, we need to calculate I first. Since this is the dissociation of the solute, for the dissociation, what's the relation? Alpha is equal to I minus 1 by N minus 1. What's the alpha mentioned? 0.9. I minus 1 by, what is the N value for the NaCl? NaCl upon dissociation giving off Na plus as well as the Cl minus. So, how many particles? It is having 2. 2 minus 1. So, then I is equal to 1.9. We got the I value as the 1.9. So, 1.9. And what is the molarity mentioned? 0.002. That's the C value. 2 into 10 power minus 3. And what is the R value? Since all the options are given in all the pressures units are in bar, R value can be taken as 0.0821. And temperature 27 plus 273, 300 Kelvin. Okay, my dear students, this is 24.6, an approximate. If this value is the 24.6, this is 2 into 1.9, 3.8. 24.6 into 10 power minus 3. Just by solving, we'll get that 0.094 bar. 0.094 bar. Coming to the next question. 0.1 formal solution of NaCl found to be isotonic with 1.1 weight by volume % solution of urea. Calculate the apparent degree of ionization of NaCl. It is mentioned that isotonic solution. My dear students, when the solutions have same osmotic pressure, we can say isotonic solutions. Solutions with same osmotic pressure. What are the isotonic solutions? Solutions with same osmotic pressure. For isotonic, what is the condition? Pi 1 is equal to pi 2. And pi 1 is equal to pi 2 in the sense, at a given temperature, we can able to write I1 C1 is equal to I2 C2. At a given temperature is not a variable. R is already constant. These two are the variables. I1 C1 is equal to I2 C2. Right. For NaCl, you are not supposed to write I value. You need to calculate I value here. I into, what is the concentration of NaCl given in formal? 0.1 formality. And I2 value for urea, this is a non-electrolytic non-volatile solute, 1 into its concentration, 1.1 weight by volume percentage, in the sense weight of urea is 1.1, molecular weight of the urea is the 60 into 1000 by 100. 1000 by 100. So, this 2 zeros cancel, 0, 0 cancel, and I value is equal to, when you bring 0.1 to the other side, it will become 10, 10 into 1.1, 11, 11 by 6, which is 1.83. What's the 11 by 6 value? 1.83. You are not asked to calculate what's the I value for the NaCl. You are asked to calculate degree of ionization of the NaCl. So that we need to calculate alpha with the help of I. Since this is the dissociation, alpha is equal to what? I minus 1 by N minus 1. What's the I value? 1.83. 1.83 minus 1 by N value. For NaCl, what's the N value? Number of the particles of the NaCl, Na plus as well as Cl minus. 2 minus 1. So alpha value will be 0.83. Degree of ionization. What's the degree of the ionization? 0.83. Look at this. Coming to the next question, my dear students. The vapor pressure of a dilute solution of the glucose is 750 mm of mercury at 373 Kelvin. The mole fraction of the solute is RLVP model, my dear students. What is RLVP? Relative lowering in vapor pressure. Vapor pressure of the pure solvent is always higher than that of vapor pressure of the solution that containing non-volatile solute. Higher vapor pressure minus lower vapor pressure. Lowering in vapor pressure by P naught for the dilute solutions by P naught is equal to mole fraction of the solute. Okay, my dear students. But here it is mentioned as vapor pressure of the solution as 750 mm of mercury. Vapor pressure of the solution 750 mm of mercury mentioned. Vapor pressure of the solvent not yet mentioned. If not mentioned, we can take height of mercury column. What is the height of the mercury column in mm of mercury? 760. If P naught value not yet mentioned, based on the units, we can able to write P naught value by taking height of mercury column. 760 mm of mercury you can take, or 760 torr you can take. Suppose if vapor pressure is in torr, 760 torr you can take. Otherwise 180 m you can take. So that 760 minus 750 by 760, which is equal to mole fraction of the solute. So 10 by 760, 1 by 76, which is equal to mole fraction of the solute. 1 by 76. Coming to the next question. A certain substance A tetramerizes in water to the extent of 80%. To the extent of 80%. A solution of 2.5 grams of A in 100 grams of water lowers the freezing point by 0.3 degrees C. The molar mass of A is, dear students, whenever dimerizes, trimerizes, tetramerizes, polymerizes, associates, like that, it is there with the question. You can understand that is the degree of association of the solute. Solute undergoing association with the solvent, right? You follow this tetramerizes, in the sense a kind of the association. 4 molecules of the A can undergo the tetramerization and giving of A4. Like that you can understand. So let us find I value here. For association of the solute, what is the relation between alpha and I? Alpha is equal to 1 minus I by 1 minus 1 by N. For the association. What is the alpha mentioned here? 80%. Alpha mentioned here. Alpha 80% in the sense 0.8. 1 minus I we need to find out. 1 minus 1 by, how many molecules of the A is the tetramerizing here? 4. So 1 minus 1 by 4 is 3 by 4. 3 by 4 into 0.8. 3 by 4 into 0.8 is equal to 1 minus I. So this is 0.6. 1 minus I 0.6. Then I value will be 0.4. For association, I value should be less than 1, no? So that I is 0.4. And here it is the depression freezing point, lowering freezing point. What's the formula? Delta TF is equal to I into Kf into molality. A value 0.4, Kf value 1.86. In general, they will give 1.86 Kelvin kg per mole. Here typo mistake, they will give 1.86. Molality we need to expand the molality. What is the weight of the solute? 2.5 grams weight of the solute by molecular weight of the solute we need to find out into 1000 by weight of the solvent 100 and delta TF mentioned as 0.3. Delta TF mentioned as the 0.3, right? Substituting these, we'll get that molar mass as 62 grams. Coming to the next question, my dear students. If the observed and normal osmotic pressures of 1% NaCl solution are 5.7 and 3 atmospheres, the degree of the dissociation of the NaCl is. Observed molar mass, observed and normal osmotic pressures are mentioned. How can we calculate Vent-Hoff factor here? Vent-Hoff factor is the ratio of observed colligative property to observed osmotic pressure to normal colligative property, normal osmotic pressure is the ratio of observed osmotic pressure to normal osmotic pressure. What is the observed osmotic pressure? 5.7 by 3, which is 1.9. Here we need to calculate the degree of the dissociation of the NaCl. Alpha is equal to I minus 1 by N minus 1. Alpha is equal to 1.9 minus 1 by N value for the NaCl. Na plus Cl minus. How many particles are there? 2 minus 1. Then alpha is equal to 0.9. Coming to the next one. The boiling point of 0.2 mole per kg solution of X in water is greater than. Boiling point X in water is greater than equimolar solution of Y in water. Which one of the following statement is true in this case? My dear students, since they have mentioned equimolar solutions, we need to go for the number of the particles because the boiling point is the property which is directly related to the number of the particles. And it is concluded that the boiling point of X is greater than Y. So that we can say that, prominently we can say that X is undergoing dissociation with the water. If X is undergoing dissociation with the water, then the number of the particles of X would increase and thereby the boiling point would increase. So that second option is the right option. When you're going through the options, Y is undergoing dissociation in the water, this is the wrong. Why? Because if Y is undergoing dissociation with the water, the number of the particles of Y would increase. It would have a more boiling point. It's not given like that. So that X is undergoing dissociation in water is the right option. Thank you, my dear students. This is U. Srinivas signing off.